Number 8. Here we're looking for the apparent weight of an object once it's in water. So the apparent weight, so just think of your object here, it's in the water. So if you have a scale, what would that scale reading be? Well, that reading would be an upward tension, so that's the apparent weight that we're looking for. But when it's in water, it will also have a buoyant force, and it will also have its regular weight. So this is an equilibrium. The forces equal 0. The apparent weight plus the buoyant force minus the regular weight equals 0. So that means that the apparent weight is equal to the regular weight minus the buoyant force. So we are given the regular weight right here, 40,000. So what we need is the buoyant force. The buoyant force is equal to rho Vg for the fluid. So the density of the fluid is right here, 1,000. The volume of fluid displaced, well, it's going to be completely in the water, so it's going to displace its own volume, which is 4. So that the volume of the object is also equal to the volume of the fluid displaced. So multiply 1,000 times 4 times 9.8, and I got 39,200 newtons. And then do the 40,000 minus 39,200, and you'll get 800 newtons, which is choice D. And then the last one, number 9. This time we have an object floating in water, and we want to know what does the object weigh out of the water. So we're looking for the real weight of the object. So it's floating with 20% of its volume above the waterline. When it's floating, we know that the buoyant force must equal the weight. Those are the only two forces acting on it. So sum of the forces equals 0. Buoyant force minus weight equals 0. This is what tells us that the buoyant force equals the weight. So for this problem, all we have to do is asking for the weight, but all we have to do is find the buoyant force. So the buoyant force is equal to rho Vg. So the density of the fluid is again 1,000 right here. We need to figure out how much fluid is displaced. Well, if 20% of the object is out of the water, that means 80% of the object is in the water. That means that the volume of the fluid displaced is equal to 80%, 0.8 times the volume of the object. Because this 80% is what's displacing the water. The 20% here is not displacing the water. So the volume of the object is right here, is 1 meter cubed. That means that the volume of the fluid displaced is 0.8 meters cubed. So plug in 1,000 times 0.8 times 9.8, and you will get 7840 newtons, which is choice D. One more note about this one is you saw that there was an object floating. You may have wanted to jump to the shortcut equation, which tells us that the density of the object divided by the density of the fluid is equal to the volume of the fluid displaced divided by the volume of the object. You can always use this shortcut equation when you have an object floating in water, just one object. But this equation would have been harder to use because it only gives you information about the densities or the volumes. It doesn't give you information about the weight of the object. So, although you could have used this, remember where this comes from. This comes from knowing that the buoyant force equals the weight. And if you're asked for the weight, it's just faster to just solve for that buoyant force directly.